Welcome to this problem walkthrough. Today, we'll examine problem number 1207, titled Unique Number of Occurrences. This problem challenges us to analyze an array and determine if the frequency of each number is unique. We'll explore different approaches and discuss their efficiency. Let's dive in. In this problem, we are tasked with determining if the frequencies of all the elements in an array are unique. Given an integer array ARR, our goal is to return true if each value in the array has a unique number of occurrences. Otherwise, we return false. The input is a single array of integers, where the length of the array is between 1 and 1000, and the values in the array range from -1000 to 1000. The output is a Boolean value, true if all the frequencies are unique, and false if they are not. To help clarify this, we'll look at a few examples. For instance, consider the array ARR equals 1, 2, 2, 1, 1, 3. In this example, the output is true. Here's why: the frequency of each number in the array is as follows: 1 appears 3 times, 2 appears 2 times, and 3 appears 1 time. When we look at these frequencies, 3, 2, and 1, we see that they are all unique. Since there are no duplicate frequencies, the output is true. On the other hand, take the array ARR equals 1, 2. The output in this case is false. Here, 1 appears once and 2 also appears once. Both numbers have the same frequency of 1, which is not unique. Thus, we return false. Now, let's consider a more complex example. For the array ARR equals -3, 0, 1, -3, 1, 1, 1, -3, 10, 0, the output is true. Let's break it down. -3 appears 3 times, 0 appears 2 times, 1 appears 4 times, and 10 appears 1 time. The frequencies here are 3, 2, 4, and 1, all of which are unique. Since there are no duplicates among the frequencies, the output is true. This example demonstrates that the values themselves can be positive, negative, or 0, but what matters is the uniqueness of their frequencies. Finally, let's review some important constraints and edge cases. The array length is guaranteed to be between 1 and 1000, and values range from -1000 to 1000. For edge cases, consider a single element array like ARR equals 1. The output is true since there's only one element, making its frequency automatically unique. If all elements in the array are the same, like ARR equals 5, 5, 5, 5, the output is also true, as there's only one unique number with a frequency of 4. Arrays with negative values, such as ARR equals -1, -1, -2, -2, -2, yield false since the frequencies 2 and 3 are not unique. Lastly, for very large arrays, like ARR equals 1000, *1000, the output is true because there's only one unique number with a frequency of 1000. These examples cover a range of scenarios to help solidify your understanding of the problem. To solve this problem, one approach we could consider is the brute force method. The intuition behind this is fairly straightforward. We manually count the occurrences of each number in the array and store these counts in a list. Then, to check if all counts are unique, we would compare each count with every other count in the list. This could be implemented using two nested loops, one loop to count the occurrences of each number and another to verify if any duplicates exist among those counts. However, this method has significant drawbacks. The time complexity is n squared, because of the nested loops, which makes it inefficient for larger arrays. Additionally, while it doesn't require much extra space, it misses the opportunity to use more efficient built-in data structures. In essence, this approach is simple but impractical for scaling to larger inputs. A much more efficient solution involves using a hash map and a set. The core idea here is to count the occurrences of each number in the array using a hash map, which allows us to track counts efficiently. Once we have these counts, we can store them in a set to automatically handle uniqueness verification. The key insight is that if any two numbers share the same count, the size of the set will be smaller than the size of the hash map. The implementation is straightforward. First, use a hash map to count occurrences of each number, then transfer these counts to a set, and finally compare the sizes of the hash map and the set. If the sizes match, all counts are unique, otherwise, they are not. This approach significantly reduces time complexity to n, as both counting and verifying uniqueness are linear operations. While it does use additional space for the hash map and set, this trade-off is justified by the efficiency and clarity of the solution. Given these options, the hash map and set approach stands out as the superior strategy due to its optimal time complexity of O(n). While the brute force method is easy to understand, it is computationally expensive and unsuitable for larger arrays. By leveraging a hash map and a set, we eliminate redundant comparisons and streamline the process. The key realization that makes this approach elegant is that checking for unique counts boils down to comparing the size of the set of counts to the size of the hash map. This simplification means we can solve the problem with minimal effort after computing the counts. In terms of trade-offs, the brute force approach is simple but inefficient, while the hash map and set approach is both efficient and scalable, with the only downside being its O(n) space usage. Overall, this chosen strategy strikes the right balance between clarity and performance, making it the best fit for the problem's constraints. To solve this problem, we need to determine if the number of occurrences of each value in the array is unique. This means that no two distinct numbers should share the same frequency of appearance. First, we start by parsing the input array, which might contain duplicate integers. For instance, consider the array 1, 2, 2, 3, 3, 3. The task is to calculate how many times each unique number appears and then verify if all these frequencies are distinct. To achieve this, we use a hash map, where the keys represent the unique integers in the array, and the values represent their counts. For the example array, the hash map will look like this: 1, 1, 2, 2, 3, 3. A hash map is particularly efficient here as it allows us to update counts and look up values in constant time on average. Once we have the frequency counts, we extract these values into a list or set. For example, the hash map 1, 1, 2, 2, 3, 3 results in the frequencies 1, 2, 3, which will help us determine if every frequency is unique. Now that we have the frequency values, the next step is to check if all of these frequencies are unique. This is where a set becomes very useful. Sets inherently store only unique elements, so we can convert the frequency list into a set and compare their sizes. If the size of the set matches the size of the list, it means all frequencies are distinct. For example, given the frequency list 1, 2, 3, converting it to a set results in 1, 2, 3. Since both the list and set have the same size, the frequencies are unique. Finally, we return the result. If the sizes are equal, we return true, indicating that all frequencies are unique. Otherwise, we return false. This approach is both efficient and straightforward, leveraging the strengths of hash maps for counting and sets for checking uniqueness. Key insights include the use of hash maps for fast frequency counting, sets for enforcing uniqueness, and the optimal use of space with an O(n) complexity. Special edge cases to keep in mind include an empty array, which should return true since there are no frequencies, and arrays where all elements are the same, such as 5, 5, 5, which also return true because there's only one frequency. These cases ensure the solution is robust and handles all possible inputs correctly. When dealing with arrays that have duplicate frequencies, the algorithm still works seamlessly. For example, take the array 1, 1, 2, 2, 3, 3. The hash map for this array would be 1, 2, 2, 2, 3, 2, and the frequency list would be 2, 2, 2. Here, converting the list to a set results in 2, which has a size of 1, while the frequency list has a size of 3. Since these sizes differ, the frequencies are not unique, and the result would be false. Regarding the data structures, the hash map, or dictionary, is critical for storing the frequency of each unique number in the array efficiently. It allows us to handle the counting process in O(n) time. The set, on the other hand, is ideal for verifying the uniqueness of these frequencies. It ensures no duplicates and performs membership checks in O(1) time. From a complexity analysis perspective, the algorithm performs the frequency counting in O(n), where n is the size of the array, and the uniqueness check in O(k), where k is the number of unique elements. This means the overall time complexity is O(n). For space, the hash map and set together require O(k) space, which is efficient given the constraints. To wrap everything together, here's the complete pseudocode for the solution. First, we check if the input array is empty. If it is, we immediately return true, since an empty array has no frequencies to compare. Next, we create a hash map to count the frequencies of each unique integer in the array. For each number in the array, we either increment its count if it already exists in the hash map or set its count to 1 if it doesn't. Once the frequencies are calculated, we extract the frequency values into a list and convert this list into a set. Finally, we compare the lengths of the frequency list and the set. If they match, it means all frequencies are unique, and we return true. Otherwise, we return false. For example, given the input array 1, 2, 2, 3, 3, 3, the algorithm generates a frequency map of 1, 1, 2, 2, 3, 3, a frequency list of 1, 2, 3, and a unique frequency set of 1, 2, 3. Since the lengths match, the result is true. This approach is both efficient and easy to understand, ensuring that the problem is solved optimally. This implementation solves the problem of determining whether the number of occurrences of each value in an array is unique. Here's how the solution works. First, we import the counter class from the collections module. Counter is a convenient tool for counting the frequency of elements in a collection, such as a list. It is particularly well suited for this problem because it allows us to efficiently compute the frequency of each unique number in the input array. The function unique occurrences begins by receiving an integer array ARR as input. The first step is to compute the frequency of each number in the array using counter ARR. This creates a dictionary-like object where the keys are the unique numbers in the array, and the values are their respective counts, frequencies. Next, we extract the frequency values from the counter object using its values method. These frequencies are stored in a view object, which behaves like a list of integers representing the count of each unique number in the array. To determine whether all frequencies are unique, we convert these frequency values into a set. Since sets automatically eliminate duplicate elements, the length of the set will represent the number of unique frequencies. We then compare this length to the length of the original list of frequencies. If they are equal, it means all frequencies are unique, otherwise, some frequencies are repeated. Finally, the function returns true if all frequencies are unique and false otherwise. This approach is efficient, with a time complexity of approximately O(n), where n is the size of the input array. This efficiency is due to the use of hashing for the counter and set operations. This solution handles edge cases such as arrays with a single element or arrays where all elements are identical. It also works correctly for arrays with negative numbers or 0, as these are valid integers. This is the Java implementation of LeetCode problem number 1207, unique number of occurrences. The solution mirrors the logic of the Python implementation by using Java-specific collections such as hashmap and hashset. It calculates the frequency of each number in the input array using a hashmap, then checks if the size of the unique frequency set matches the size of the frequency values. This ensures all frequencies are unique. Key differences from Python include type declarations and the use of Java standard library collections. To solve the unique number of occurrences problem, we start by analyzing the given input, which is the array 1, 2, 2, 1, 1, 3. The first step is to count how many times each number appears in the array. Using Python's collections counter, we can quickly calculate these frequencies. For this input, the number 1 occurs 3 times, 2 occurs 2 times, and 3 occurs once. This gives us the frequency dictionary 1, 3, 2, 2, 3, 1. Once we have the frequencies, the next step is to extract just these frequency values into a list. From this dictionary, the frequencies are 3, 2, 1, which represent how often each unique number appears in the array. Now that we have the frequency values, the next step is to determine whether all these frequencies are unique. To do this, we convert the list of frequencies into a set, which automatically removes duplicates. The set of frequencies for this example is 3, 2, 1. By comparing the length of the original list of frequencies, which is 3, to the length of the set, which is also 3, we can confirm that all frequencies are unique because the lengths match. Since there are no repeated frequencies, the result for this input is true, meaning it satisfies the condition of having unique occurrences. For the second example, we are given the input array 1, 2, 2, 3, 3, 3, 4, 4, 4, 4. The first step is to count the frequency of each number. Using counter, we find that 1 appears 1 time, 2 appears 2 times, 3 appears 3 times, and 4 appears 4 times. This gives us the frequency dictionary 1, 1, 2, 2, 3, 3, 4, 4. From this dictionary, we extract the frequency values into a list, which results in 1, 2, 3, 4. These frequencies represent how many times each unique number occurs in the input array. Next, we check whether these frequencies are unique. Converting the list of frequencies 1, 2, 3, 4 to a set results in 1, 2, 3, 4, which removes any duplicate values. The length of the original list of frequencies is 4, and the length of the set is also 4. Since the lengths are equal, we can confirm that all frequencies are unique. This means the output for this input is true, as it meets the condition of having unique occurrences. In the third example, the input array is 1, 1, 2, 2, 3, 3, 4, 4. Using counter, we calculate the frequency of each number. 1 appears 2 times, 2 appears 2 times, 3 appears 2 times, and 4 appears 2 times. This gives us the frequency dictionary 1, 2, 2, 2, 3, 2, 4, 2. Extracting the frequency values, we get the list 2, 2, 2, 2. When we convert this list to a set, the result is 2, as all the values in the list are the same. The length of the original frequency list is 4, but the length of the set is only 1. Since the lengths are not equal, it means that not all frequencies are unique. Therefore, the output for this input is false, as it does not satisfy the condition of having unique occurrences. To analyze the time complexity, let's break the solution into its main steps. First, we use the counter class from the collections module to compute the frequency of each element in the input array. This operation involves a single pass through the array, where each element is hashed and its count is stored. Since we process each element once, this step has a time complexity of O, n, where n is the size of the array. Next, the values method is called on the counter object to extract the frequency values. This is an O1 operation because it simply provides access to the underlying data structure without performing any additional computation. Finally, we convert these frequency values into a set to remove duplicates. Constructing the set involves iterating through the frequency values and inserting each one into the set. In the worst case, where all frequencies are unique, this step requires O(m) time, where m is the number of unique elements in the input array. However, since m is always less than or equal to n, this step simplifies to O(n). After constructing the set, comparing the lengths of the frequency list and the set is an O1 operation. So, the overall time complexity of these steps is dominated by the O(n) operations. Now, let's look at the space complexity. The first major contributor is the counter object, which stores the frequencies of each unique element in the array. In the worst case, every element in the array is unique, so the space required is proportional to the number of unique elements, m. This gives a space complexity of O(m), where m is less than or equal to n. Next, the set used to store unique frequency values also requires space proportional to the number of unique frequencies. In the worst case, if all frequencies are distinct, this again requires O(m) space. Additionally, we use some intermediate variables, such as frequency_count, frequencies, and the set. However, these variables require only a small, constant amount of space compared to the space required for the counter in the set. Combining these factors, the total space complexity is determined by the larger contributors, which are the counter and the set. Thus, the overall space complexity is O(m), where m represents the number of unique elements in the input array. Comparing this optimized solution to a brute force approach highlights its efficiency. A naive solution would involve manually counting the frequencies of elements, storing them in a list or dictionary, and then performing pairwise comparisons to check if all frequencies are unique. This approach has a time complexity of O(n) squared, due to the pairwise comparisons, which becomes impractical for large arrays. In contrast, the current solution optimizes this process by leveraging a hash table to count frequencies and a set for uniqueness checks, reducing the time complexity to O(n). The space complexity is also improved, as it only requires O(m) auxiliary space for the counter and set, where m is the number of unique elements. From a mathematical perspective, each key operation, counting frequencies, constructing the set, and comparing lengths is O(n), or better, and since these steps are performed sequentially, the overall time complexity remains O(n). For the space complexity, the auxiliary space usage is proportional to the number of unique elements, leading to O(m). When analyzing different cases, we see that in the best case, with only one unique element, the operations are minimal and require O(n) time and O(1) space. In the average case, with m unique elements, the time remains O(n) and space O(m). In the worst case, where all elements are unique, m equals n, resulting in O(n) time and O(n) space. When solving this problem, there are some common mistakes that can trip you up if you're not careful. First, forgetting to handle edge cases like empty arrays or arrays with very few elements can lead to unexpected errors or incorrect results. For instance, if the array is empty, there's nothing to count, and your logic might fail unless you explicitly account for this. Another frequent mistake is using nested loops to compare occurrence counts. While this might seem straightforward, it leads to a time complexity of O(n squared, which becomes extremely inefficient for larger input sizes, such as arrays with tens of thousands of elements. Misusing frequency dictionaries is another issue. This could involve failing to initialize keys properly or accidentally overwriting values, resulting in incorrect frequency counts. Additionally, overlooking problem constraints, such as a limited value range, can prevent you from leveraging smarter optimizations. For example, if the values are bounded between 1 and 100, you could use an array for counting instead of a dictionary, which might be faster in some cases. Finally, skipping the crucial step of checking for duplicate counts can lead to false positives when verifying uniqueness, so make sure to use tools like sets effectively to avoid this pitfall. In interviews, it's essential to go beyond simply solving the problem and demonstrate a deeper understanding of the constraints and trade-offs. For example, carefully analyzing the input size and value range allows you to choose the most efficient approach. If the value range is small but the input size is large, using a counting array might outperform a dictionary in terms of both speed and simplicity. Interviewers also appreciate when you clearly communicate the trade-offs of your decisions. For instance, you might balance an O(n) solution that uses extra space against a less efficient approach that minimizes memory usage. If the constraints allow for it, you can even optimize your solution early. For example, if the input is guaranteed to be sorted, you might simplify the logic significantly. Finally, always emphasize the importance of testing edge cases. Show that your solution handles scenarios like empty arrays, arrays with just one element, or arrays where all elements are identical. This demonstrates thoroughness and a strong problem-solving mindset. It's also helpful to understand how this problem relates to others, as this can deepen your understanding and prepare you for variations. For instance, LeetCode 1-2 sum is a classic problem that highlights the use of hash maps for efficient lookups, a technique that's also valuable here. LeetCode 347, top k frequent elements, shares similarities in counting frequencies and focusing on performance optimizations. Another related problem is LeetCode 380, insert delete get random O(1), which illustrates how leveraging the right data structures can enable unique operations efficiently. Of course, LeetCode 1207, the unique number of occurrences problem itself, is directly related, as it focuses on verifying the uniqueness of frequency counts. By studying these problems, you'll notice common patterns and techniques that can be applied across different scenarios. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is a sorting-based approach. By sorting the array first, you can group and count values consecutively, which simplifies the logic. However, this method has a time complexity of O(n log n), making it less efficient than hash map solutions for very large inputs. Another alternative is using an array for frequency counting, which works well when the value range is small, such as 1 to 100. This reduces space complexity compared to hash maps, but it's less flexible if the value range becomes larger or less predictable. Finally, the hash map and set combination is often the most efficient solution for large arrays. The hash map handles frequency counting in O(n) time, while the set ensures uniqueness verification. The trade-off here is the additional space required for the hash map and set, but this is a small price to pay for the performance boost when dealing with large inputs. Each approach has its strengths, so understanding the trade-offs is key to selecting the best one for the given constraints. Great job following along. Today, we solved unique number of occurrences using hash maps and sets for an efficient solution. Remember the importance of mastering these data structures for frequency and uniqueness problems. Thanks for watching, and stay tuned for more problem-solving tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!